should have come with you.
Oh, bar. People I was working with, guys were saying go through. I don't think that's people that they employ will sit there controlling you and making sure you pay. Shit. They were just opening your eyes. Through test. It wouldn't be quick test. It's just a little bit creepy around. So people are, you're aware of people moving around.
Do we start on time or do we usually wait for emails?
Oh, so you would like to be fired.
Yeah,
Really full out. I'll make, oh yeah. Right, see you for lunch.
Please come in and be seated. We'll be starting the workshop in 1 minute. Thanks. Okay, great. Let's get started. Hello, everyone. Welcome to the ACM RRTF Applied Networking Research Workshop. I'm Francis Yan from Microsoft Research, and here with me is Maria Apostolaki from Princeton University. Thank you all for being here and for participating in our workshop. As you know, ANRW is more than a workshop. It provides a wonderful opportunity and a unique forum for everyone who's interested in applied networking research from the world to come together to share insights, experiences, and exchange ideas. It's also a bridge between IETF and academia. So we hope that by attending today's workshop, you will not only find it intellectually stimulating, but also professionally rewarding as you make connections with people like-minded. We have a full day of events and with many insightful research papers, a keynote, and a panel discussion. However, before we officially get started, we are required to present to you some IRTF policies. So first of all, since ANRW is not a research group within IRTF, the intellectual property rights disclosure rules from IRTF do not apply to ANRW, which means that you are not obligated to disclose intellectual property relating to the presentations or the contributions made to ANRW. And the audio and video of this workshop will be recorded and posted online. And you agree to be recorded unless you indicate otherwise. And finally, by attending this workshop, you agree to the privacy policy of IETF, and you need to adhere to the code of conduct. Okay, so let's get back to the main agenda today. First of all, Maria and I would like to thank all our PC members. So we have 22 people on the PC this year, and together they have done a fantastic job writing 64 reviews for 21 papers. And among the 21 submissions, we have accepted 11 papers. So that's about 50% acceptance rate. We're right on target. Thank you all for their contribution and service. We'd like to also thank our support team, Colin, Amy, Alexa, and Greg. Especially a big shout out to Colin, who's the IRTF chair and is chair of the steering committee of ANRW. We couldn't have pulled this off without your help. And next slide. Start working. 1 second. Could you maybe press the right button? Yeah, it's not working. If you press right button, does it work? No. We have some technical issues. 1 second. It's not working. Maybe reshare. Stop sharing and reshare. Now we can reshare. Sorry about that. Your internet connection. So if you disable Wi-Fi, then you should have. Yeah. Now it's coming back. Turn off the. All right, it's working again. Let's go back to here. Okay, next, we'd also like to thank our sponsors, Comcast, Akamai, and Netflix for their generous financial support for the travel grants. Thank you. And here's the overview of today's agenda. We're in the first session, and we're going to start with a keynote, followed by research papers on IoT, programmable networks, and network measurement. And in the afternoon, the second session, we're going to have additional papers on network measurement, along with papers on security and privacy. In the last session of today, there will be papers on DNS and BGP. So depending on your interests, you could select to attend some of the sessions, or you're encouraged to attend all sessions. And with more details, it's our pleasure and honor to have our guest speaker, Professor Phil Levis from Stanford University. He was also my PhD co-advisor back there. He will deliver a keynote. It's the end of DRAM as we know it. Then there will be 3 research papers on IoT location impact, on programmable infrastructure for networking, as well as reflections on active network measurements in academia. In the second session, we will have papers quantifying the effects of TCP options, QUIC, and CDNs on throughput, mapping the Ukrainian refugee crisis using internet measurements, and security and privacy research opportunities for IETF protocols. After that, we will host a panel discussion moderated by Maria with Lisha Zhang from UCLA, Chris Wood from Cloudflare, and Yog Ott from TUM. And the panel will be about what do we want the internet to look like in 20 years. In the last session, many papers on BGP and DNS. So we're going to learn how to learn the barriers to work with public RAR level data, and call for collaboration DNS integrations, repeatable name resolution with full dependency provenance, enabling multi-hop ISP hypergiant collaboration, and last one, practical anomaly detection in large BGP-related VPN networks. Finally, some logistics. The complete program agenda of today and the PDF of each paper can be found on the ANRW-23 website. And the presentation videos of today will be made available on the same website after this meeting shortly. And for Q&A, we kindly ask you to join the queue by logging into MeetEcho if you have a question for the presenter, whether you're in person or remote. So we kind of have this single shared queue for both remote and in-person participants because, for fairness reasons. And as networking people, we care a lot about fairness and queuing policies, right? So we have implemented this FIFO queue with drop tail policy, which means if you're at the end of the queue and we run out of time for that presentation, you will be dropped like a packet. But you should always, feel free to follow up with the presenter after the presentation. And the meeting links to each session, the MeetEcho links, can be found on the IETF agenda or the specific page for NRW. Okay, now before I hand over my microphone to Phil Levis, let me just give a brief introduction of him. So Phil is a professor in the CS and EE departments of Stanford University. And as I said, he was my PhD co-advisor there, and it was a great pleasure working with him for 5 years. And Phil's research generally spans, operating systems, networks, software design, especially for embedded systems. And the results of his work have been running on hundreds of thousands of devices and served as the basis for internet standards. So Phil is no stranger to IETF. And moreover, his research has been recognized by 4 Test of Time awards, which speak for the long-lasting impact of his research on our networking community. And with that, let's welcome our keynote speaker, Phil. Phil, please take it away.
All right. Yeah, so Francis asked me for an exciting or interesting talk, so I tried to come up with an exciting or interesting title. So giving this talk to a group such as this, if there are folks of you who work in hardware, I would love to hear your thoughts. Tell me that I'm wrong. Please also ask questions at any time. So as the title sort of suggests, I'd like to apologize first, which is I used to research networks a long time ago. As Francis mentioned, for example, stuff that I worked on became part of Ripple. There's some RFCs. It didn't work in security, TLS RAR, congestion control with Francis, video streaming, and with Puffer with Francis. I actually haven't done much networking research in the past few years. So I don't have a lot of cool, interesting, cutting edge networking stuff to talk about. So I apologize. But instead, I want to talk about something which I have found really interesting and has been very confusing to me as somebody building software at the edge of the networks or at the end devices. And I think it's this interesting shift in what's happening technologically, which is going to have huge implications to the applications on the internet. And so I hope you do too. So here's the basic summary. Our networks are going to get faster, our processors are going to get faster, but we're not going to get more RAM. The cost per bit is flat. It's been flat for 10 years, if you haven't noticed, and it's not going to go down. The performance of RAM is also almost there, but it's also going to flatten in probably the next generation. Both it's been flat in latency for a long time. It's going to flatten in throughput unless there are some really huge shifts, and it's not clear where they'll happen. We'll see. What this means is if you look 10 years forward, computers are going to be really different. And so will their applications. And so kind of the tagline is it's the end of DRAM as we know it. There we go. Great. Yeah. Okay, good. So here's the summary for the rest of the talk. I'm going to explain what's happening with scaling. Why is it that RAM isn't getting cheaper? Why is it not going to get cheaper? Then I'm going to talk about what's happening with its performance. What's happening with latency and throughput? Why isn't RAM latency going down? In fact, why is it going up? If you have an L3 cache miss, it's going up. And also why throughput is going to go up for a little while, but not much longer unless there's some really big shifts where it's unclear they'll happen. What this means going forward is there's going to be 3 kinds of memory in our computers. And I'll talk about what those are and what their properties are. And at the end, I'll talk about a little twist, sort of this evolution of the PCIe bus, CXL, Compute Express Link, and kind of how that will change things in a bunch of ways. So let's start at the beginning. Why is RAM not getting cheaper? So here's a plot of versions of DDR. 6 is still hypothetical. It's in work at JEDEC. So here's DDR1 through DDR5. And what you can see is over the past 22 years, the throughput has gone up tremendously. There's some latency improvements in the beginning, but for the past 3 generations, cost has been flat, cost per bit. If you look at sort of a standard size DIMM and the amount the DIMM costs, and you compute cost per gigabyte, it's been $2 to $3. Now there's huge variations in this in time because the RAM market is very sensitive, supply and demand. But if you sort of average it out, you get $2 to $3. So for example, a few months ago, even DDR5 was very expensive because there's a shortage of it. Now there's plenty of it, so it's cheaper. But if you just kind of average out, cost is flat. So one way you see this manifest is if you read recent papers from many of the hyperscalers. They say, hey, RAM is 40% or 50% of the cost of a server these days. And it's going up. And it's been going up. And that's a big concern. You don't want to build a server when it's 90% of its cost is RAM. So why is this? Why is this happening? I think the basic summary is a DRAM bit is a transistor, right, and a capacitor. And that's it. Like, you can't make this circuit much simpler. It's about all you got. And so unlike with a processor where there's lots of design flexibility, the cost of RAM is basically the cost of manufacturing transistors. And if we look at the cost of manufacturing transistors, somewhere around 28 nanometers, it became flat. The cost of actually manufacturing a gate stopped going down. So we continue to be able to make smaller and smaller gates. We can continue sort of Moore's law. Dennard scaling is dead. We can keep on going to new, smaller and smaller nodes, but the cost per transistor of manufacturing is not going down. So I can make you DRAM that's twice as dense. It just costs twice as much. It's the same cost per bit, because again, a DRAM cell is just a transistor. And so for a really long time, all of computing was able to chase, this exponential decrease in cost, right? So when a new process appeared, we would move to the new process because, gosh, suddenly all of your existing things cost, say, half as much to make, right? You sort of reduce the size, you get twice the transistors per unit area. Great, everything is twice, costs half the amount to make. Therefore, you move to the new process. Great, and that then gives you those savings on everything that you're selling. But this has basically ended. And you talk to architects and they say, oh yeah, didn't you know? And it turns out lots of people didn't know. And we're now kind of fighting this fixed cost per transistor. And so here's sort of, if we sort of chart the size of process nodes, over time, something happened right at 28 nanometers. That's when suddenly this scaling stopped. So what happened? So 28 nanometers is when we went from planar transistors to FinFETs. So basically things are getting so small, we need more surface area to be able to actually control, the voltage across the gate. And so this is when gates started becoming three-dimensional. And so they started becoming more expensive to make. So these next nodes, like the next ones that TSMC is putting out, even FinFETs aren't enough. We have gate all around, where suddenly there's multiple fins or cylinders, because you just really need to affect the surface area to volume ratio to control the gate. So making these transistors is getting really, really hard, harder and harder. It's not just simple scaling, you need new processes. Right, and so basically above 28 nanometers, we used planar gates. Now we're using FinFETs, and soon gate all around, GAA. And the other problem is that as we make our gates smaller and smaller, it gets harder and harder to actually do the manufacturing. So this is totally like a physical manufacturing engineering problem. So if you look at sort of the number of steps it takes to produce, a die at different sizes, you realize, wait, like just going as we're getting to smaller and smaller nodes, just the amount of cleaning you have to do, the number of other steps and processing steps you have to do is just going up. So we can put more transistors onto a die, but gosh, we have to now suddenly run many more processes in order to actually produce them. It's not just turning a crank and scaling the process down. And this has all kinds of other implications as things get smaller and smaller. So here's sort of a nice chart of, now allowable 20 nanometer particles per milliliter of chemicals. And in 2022, it's going under 1, right? So you can have like you can even have 1 20 nanometer particle in your chemicals. So everything has to be cleaner, everything has to be better. It's getting harder and harder. And it's not just that. So, we make dyes and chips through lithography. So basically, you put a mask and you shine light, and then you do a process where, gosh, where the light shine, we can then strip that stuff off. And there's all kinds of steps in how you do this with etching and metal, et cetera, et cetera. So if we go to sort of patterning below 28 nanometers, if you look at the frequencies of light, basically there's a point where we stop being able to use visible light or ultraviolet light. We're now at the point where we're using extreme ultraviolet light, so 10 to 100 nanometer wavelengths. So way out there on the spectrum. And so one of the problems with extreme ultraviolet light is that everything absorbs it. So the system has to operate in a vacuum. You can't have any lenses. because the lenses will just absorb the light. So everything is through mirrors. And so this diagram on the bottom in the center shows you kind of the series of focusings that go on through a long series of mirrors within an extreme ultraviolet lithography process. And that's what you see also on the bottom right. That's an actual shot from an EUV lithography device. So the process to make these is pretty crazy. And I'll talk a little bit more about that. Just to give you an idea, like what it even takes to make the light, to make these transistors at this scale. So the system is dropping tiny droplets of molten tin, which then get zapped with one ultraviolet laser, which causes these droplets of tin to expand out into like a disk, which then they can get zapped by another laser that's even more powerful, which then gets them to produce 13.5 nanometer light. This is happening 50,000 times a second. So the process that goes even to make the light for this kind of manufacturing is, you can understand why it's expensive. And I mean, you should, if you ever have an opportunity, you should go read about how this works, because whenever I do, it just boggles the mind to me, like the kind of engineering that goes into this. As one person puts it, you know, the precision of this lithography is so good that if we were shining a laser at the moon, like we could hit a quarter, right? Because it has to be at these scales. For 20 years, people really wondered whether it was even possible, whether this was a possible engineering feat. It took, you know, tens of billions of dollars, 20 years of research, but as another person puts it, there is no plan B, right? If they couldn't do it, then we would stop being able to make chips smaller. So they made it happen. But so the brief summary of all this, of what the crazy engineering that's going on behind lithography today is, we can continue to make smaller transistors, but the per transistor manufacturing cost is flat because of the degree of engineering that's required to do so. So if DRAM costs are flat, why aren't CPU costs flat? We do see bigger CPUs, faster CPUs. So the short answer is the per core cost is going down slightly. So here's just a series of AMD server class processors, Rome, Milan, Genoa, and Bergamo. Cores are getting faster. You have better accelerators, all kinds of stuff you can do in the design. It's also the case that design is a larger fraction of the cost of CPUs. A lot of design work goes in there, unlike, say, RAM, which is mostly manufacturing and very thin margins. So there's stuff you can do with CPUs to use your transistors more effectively, right, in order to improve performance. Chiplet designs, for example, is what, you know, AMD has been doing for a while. Makes design a lot less expensive. Rather than designing one big chip, you're designing little chiplets and then stitching them together on an interconnection fabric. So they're coming up with ways to make the whole process of designing the chip cheaper, which then means that, gosh, we can continue to have faster chips, sort of, right? You can see sort of the cost of the processors is going up. So in summary, the price per bit of DRAM, it's not going down soon. It's basically the cost of manufacturing transistors. There isn't much flexibility here. The cost of producing transistor spending is going up because it's getting harder. So what that means is if we want new RAM that has lots more bits, we're not going to get it with how we make it today. We're going to need new materials. You could do it through some like new fancy material, who knows what. There's nothing on the roadmap, right? So even if something appeared tomorrow, we're not going to get it for 10 years. I was chatting with somebody who's talking with Micron, and the way the Micron person put it was, yeah, we've, you know, the periodic table, we've tried everything, right? There's no material coming down the pipe. So there's the Intel Optane memory, which unfortunately was just, you know, was pursued for, was it 8 or 9 years, and with Micron, it was just shut down. So that was an idea of, hey, maybe we can do things a bit differently. That gave you a 2x density improvement. Turned out that wasn't quite enough for the market. You know, maybe it'll return as pressures get harder. It's also non-volatile. There's a bunch of other things, but maybe Optane will come back. We'll see. So there are maybe some long shots. So RAM basically requires one lithographic step, you know, per sort of layer, unlike Flash, where you can, kind of the magic of Flash is you can make many, many Flash bits with a single lithographic etching step, right, or a single lithographic step. Basically, you're making bits down in the Z-axis or in the Y-axis. Maybe somebody will come up with some fancy way of making DRAM where we can, with a single lithographic step, make multiple layers. that would, that will be a pretty amazing thing, and whoever does that and patents it will make bajillions. So people are trying. I don't know if it'll happen, but that would be something which can maybe change this. We'll see. So one thing is that DRAM is flat because you think just how highly engineered it is. It's this very simple circuit. Let's just make it as dense as we can. Processors and networks still have some runway. So generally NICs are a few nodes behind other processes. And there's still lots of room for acceleration in CPUs. If you look at a modern CPU like a Sapphire Rapids, there's a ton of accelerators in there. And I think we're going to see that continue because that's how you get efficiency in terms of compute per watt. Dun, dun. Next. All right, great. Again, if anyone has any questions or thinks I'm wrong, please tell me. You're welcome to come up. So, wait, did you get the next? There we go, great. So that's cost per bit, so that's capacity. Let's talk about latency and throughput. So again, let's go back to this table. Here's DDR through DDR6. And so you can see latency is flat, right? So, I mean, it's going down a little bit, 79, 74, 72. So why is that? So first of all, well, the actual latency of the DRAM of the DIMM itself is going down slightly. The observed latency of a processor is going up. So here's, for example, just looking at a series of 4 generations of Intel processors: Skylake, Cascade Lake, Ice Lake, Sapphire Rapids. The observed latency of an L3 cache miss hitting main memory is going up from 87 to 142 nanoseconds. So the reason for this is these processors are getting bigger, right? And they have more cores and they have larger caches. So the cache miss rates are going down. So the overall performance is going up, right? If you have good speculation or prefetching, whatever it is. But the observed performance of an L3 cache miss, so think like random lookups through a hash table, the latency is going up. Of course, you've got lots of cores, your throughput still goes up, in that case, but from a latency standpoint, it's going up. And so if you look at like what a Sapphire Rapids, sort of just came out a few months ago, processor looks like, it starts to kind of become clear. So here's a Sapphire Rapids die. And so it has a whole bunch of CPU tiles on it. It's got its memory control tile. Each CPU has its own L1 and L2. Then there's this shared L3. You can see all the connections on it. There's the PHY for talking to other dies for, sort of the interprocessor, the intercore interconnect, PCI lanes, UPI, all kinds of stuff. Of course, the chip is 4 of these dies all stitched together. And so, if you're accessing L3, well, an L3 miss, then you're going to have to go across this entire chip to see if it's there. And then if not, you might have to also progress depending on where the DRAM is hooked in on these memory control tiles, right? You're going to have to go potentially further. So there's no question that overall performance throughput is going up, but there is this throughput latency trade-off. So let's talk about the throughput of the DIMMs themselves. So this is kind of the performance you can get from sort of the top end, speeds of DDR. So say if you have like a modern DDR5, you can get something like 57 gigabytes per second out of a DIMM, right? And sort of that's a theoretical maximum. Of course, in practice, it'll be a bit lower. So that turns out to be 7.2 gigatransfers per second. So this gets now into sort of how these signaling on these DIMMs actually work. So it turns out that DRAM data lines are single-ended, right? So it's just a single wire. Unlike clock lines, which are differential, there's 2 lines, right? So it turns out in differential signaling, we really know what the limit is, which is if you try really, really hard and you put a lot of money into it, you can do 200 gigabits per second. You can achieve that. 100 is pretty straightforward with really good engineering. 50, yeah, you can just do. But it's really tough to go past 200. At some point, you're talking about 5 picoseconds. Gates only switch so fast. Single-ended, though, it seems like maybe the practical limit is around 9.6 The reason is with differential signaling, you're just comparing two lines, right? You can say which one is higher. Is it 0 or is it 1? If there's some interference or any kind of noise or some kind of sort of swing on both the lines, both of them see it and you're fine. With single-ended though, you just have one thing, you're comparing to a reference, and it's really, really tough to keep that stable. So 9.6 gigabits per second for a single data line. So DDR6 is trying to push this further with some buffering, right? So maybe you can allow the signal to stabilize, but that also increases latency. And so the brief summary is DDR latency is not going down. If anything, we're going to see its latency going up a bit due to more complex caches. DDR is also reaching its signaling limit. So the hope is DDR6 can do 12.8. I hear people say they think 9.6 is sort of the practical limit to engineer this. Maybe you can go to 12.8 by adding this buffering, adding some latency, we'll see. So there is one escape hatch on this, which is we could shift from single end to differential signaling on DRAM. So we could have two data lines and just do the compare. This would require completely new DRAM designs. If you look at JEDEC, there's no current plans to do this. Maybe they will, we'll see. There's some historical concerns about this of like whether there's, intellectual property stuff. It's the IETF knows how to navigate well, but there's also some concerns about maybe going to differential signaling. So we'll see what happens. But if that happened, then maybe we get some more throughput. We're not going to get better latency, but we'll get better throughput. So in summary, right, the cost per bit of DRAM isn't going down anytime soon. I'd say at least 10 years, and then who knows how long. DRAM latency is not going down either. DRAM bandwidth is going to go up a bit, but there isn't much room left. Even if DDR6 or 7 or 8 does go to differential signaling, this is going to be like 5 years out at the very earliest, which means earliest 8 years before you can buy it. And all this really just boils down to the scale at which these things are operating and really just like the low level EE signaling and all that kind of stuff that's going on. Okay, so what does this mean if DRAM is flat? What's going to happen to memory? So one way to look at it is that when we hit clock frequency as a limit, and so the end of the 90s, we couldn't really get much higher than 3 gigahertz in practice for the designs. What happened? Well, we went to multi-core, right? So we hit some physical limit, and then systems just moved in another direction. And so what happens if DRAM's capacity, latency, and throughput are flat, but everything else, your network and your processor, continue to get faster? So just a little sort of back of the envelope calculations here. So today it's pretty straightforward to get a 200 gig NIC. 400 gigs will be soon. So at 400 gigabits per second, a 4 kilobyte packet is 80 nanoseconds. So it's less than an L3 cache miss. And at 400 gigabits, a 64 byte packet is 1.25 nanoseconds. So these are really, from a software standpoint, these are really crazy time scales. Furthermore, if you look at a modern server processor and how much aggregate DRAM bandwidth it has, 400 gigabits is 10% of that. So that means that if I wanted to just simply echo packets, right? So write the packet into DRAM, then read the packet out of DRAM, that's going to be 20% of my whole system memory bandwidth. And you see the implications of this in some, high performance systems that people build. So this is a nice slide deck from FreeBSD conference 2021, Netflix, on how they stream 400 gigabits per second, in their open connects in their devices. And sort of they make this interesting note. There's this 4x memory amplification, right? They have to DMA data off the disk into memory. Then they have to read the data from memory into the CPU. Then they have to write the encrypted data back into memory and then DMA the data from the memory back to the NIC. And that's just assuming there's no compression or other processing going on. This is like a 4x cost on the memory bandwidth. So don't think the two I said before are 20%, think 40%, just to stream stuff. And I remember I was chatting with an engineer at Google who was talking about some high performance stuff they do, and they said, look, we architect our pipeline so that the data enters the cache only once, because anything else, and it's a bottleneck. So given this, there's this flip side, which is if cost per transistors is flat and we can't, new nodes are becoming more and more expensive, the way that CPUs are going to give you performance the way they do today even is through accelerators, computational accelerators. So you look at, for example, Sapphire Rapids, and there's a whole bunch of new accelerators. Things to make analytics faster, things to make memory copies faster, things to do all kinds of stuff with matrices, right, for sort of preparation for machine learning. So in the end, in silicon, compute is cheap, moving data is expensive. So we can make things blazingly fast, but then the challenge is, how do you feed it? So you can, for example, add lots more ALUs under your processor. They're cheap. You can add all kinds of accelerators that allow you to do computations really fast over large amounts of data. But at some point, you can't feed the accelerator fast enough. I mean, DDR doesn't have enough bandwidth to match the computational speed of a CPU that has a lot of accelerators in it. And in fact, you see this today. If you look at a GPU, right, or a TPU, they don't have DDR, right? They have high bandwidth memory, HBM. And so what's high bandwidth memory? It's basically DDR with a lot more data lines. So DDR5 is 64 data lines. HBM3, which is like on the NVIDIA H100, has 1,024 data lines. So 16 64-bit wide channels. The trade-off here is latency is higher, right? Like 300 nanoseconds or so. But if you're streaming huge amounts of data, like if you want to stream megabytes of data or hundreds of megabytes of data, you don't really care about those hundreds of nanoseconds of latency. So one of the challenges, and again, this gets back to this idea, this is about like manufacturing and the physicality of these devices and how signals work. You can't run 1,024 copper traces from your memory module on a printed circuit board, generally speaking. So practical kind of thinnest traces you can make today, maybe 0.152 millimeters. So if you have 1,000 of those, that's like 155 millimeters of just trace without even spacings between them, right? So that's much bigger than your chip. You can't do it. So instead, the way you integrate an HBM with a processor is in silicon. So you basically make effectively like a PCB, a printed circuit board, in silicon, because then you can do things at lithographic scales, something called an interposer. So you have your processor that's built with its particular node, its particular manufacturing process. You have your memory module made by, say, Samsung with its particular manufacturing process. They can be different nodes, doesn't matter. Then they have, pads, and then you join them onto this interposer, which is like a little silicon scale PCB to connect them, right? So it works, it's great, it's expensive, right? So we now have these two parts, we have this third part, we have to manufacture them, we have to, actually assemble them, and, it turns out you can have lots of failures. But you can do it. There's also why GPUs are expensive. It's also why, for example, the Sapphire Rapids Max that has integrated HBM, it's an expensive high-end processor. So in fact, the most recent Intel processors, they have a model of the Sapphire Rapids with an integrated 64 gigabyte HBM module, which is kind of interesting. And so the idea is, hey, if you're going to be doing something that's actually arithmetically really intensive over large blocks of data, you can buy an Intel processor that has an HBM module and then stream out of that. So coming to a processor near you. My guess is this is going to continue, because at some point, if we put accelerators into our processors, the only way you can feed them fast enough is with HBM. So HBM is interesting because it allows you to sort of circumvent these bandwidth concerns per pin, et cetera, really get much higher bandwidth out of your memory. But it raises an interesting point. So if we look at kind of a modern memory hierarchy, from registers to something like a hard disk drive, where does HBM sit in this hierarchy? And the short answer is it kind of doesn't, right? It has higher latency than regular DRAM, but it also has much, much higher bandwidth. than regular DRAM. So it's not in this strict hierarchy of, small and fast to big and slow. It's also a limited size, so 64 gigabytes rather than like half a terabyte or a terabyte. So I think going forward, we're going to see like this pressure on DRAM and the need for higher bandwidth to be able to process this stuff is going to push systems towards three types of memory. The first is, DDR that we know and love. So think of this as latency optimized memory. So this is the memory where a random access has the lowest latency that we can get for something of significant size. We're not talking about like SRAM caches or something like that. So think hundreds of gigabytes, maybe a terabyte of RAM, 100 nanosecond latency, bandwidth on the order of 50 gigabytes per second. We also have capacity memory. So this is basically flash, right? So today latency is in the 100, like under 100 microseconds. I think that can actually come down a lot. A lot of that is your FTL layer. Maybe 10 microseconds seems feasible if we push hard enough. Bandwidth in the tens of gigabytes per second and the size of terabytes. So this isn't that strict in the hierarchy I showed before. These are what we think of as like, oh, the smaller and fast and the bigger and the slower. But then the third kind is bandwidth. So memory that's optimized for throughput. So this is HBM today. So think tens of gigabytes, hundreds, so multiple hundreds of nanoseconds of latency, but bandwidth in say 800 gigabytes per second. HBM3 module can do 800 gigabytes per second. So more than the aggregate memory bandwidth of all of the DIMMs attached to your processor. And so if we look forward, this pressure is going to really push us to have machines that have this mixture of memories, latency, capacity, and bandwidth. Each of them is tied to a different compute element. For example, capacity elements, usually are tied to the CPU. That's where our disks are attached. But perhaps it's attached to the IPU, the SmartNIC, or the DPU. Our latency memory, of course, things like our SmartNICs have some, but it's mostly in the CPU. That's where our, say, terabyte of RAM lives. Now, bandwidth memory, well, we're seeing it appear on CPUs. It's been on TPUs and GPUs for a long time. But part of things from a networking standpoint, so networks are increasingly going to want to transmit data to get it into bandwidth memory, basically for accelerated processing. So we're seeing this today when you're doing, training within a data center. You're shipping huge amounts of data to nodes, then they can do their training on the TPU. And so what does our networking stack look like when really what's going to happen is we're going to load our memory into the DRAM on a SmartNIC before we then offload it, to a GPU's high bandwidth memory? Is there going to be a point where our NICs actually need high bandwidth memory in order to be able to get stuff back and forth fast enough as the NICs get faster and faster? So this is my hypothesis about where computers are going. And I think there's one interesting twist, which maybe some of you probably heard a bunch about, Compute Express Links CXL. And so it turns out the speeds and the capacities that we're talking about, the workhorse of the backplane for most sort of servers and desktops and stuff and laptops today is PCIe, right? PCIe Express. So one of the problems with PCIe is that it's high latency. So basically, depending on who you ask and speed, the minimum latency to do like a PCIe operation is around 800, maybe 500, nanoseconds or so. So when we think of this, is if you've got a 400 gigabit NIC, that's 40 kilobytes of data. That's a lot. And so you could think if you have like some 8 kilobyte jumbo frames, that's 5 of them. It's just the time to even talk to the NIC. That being said, PCIe is pretty high throughput. So PCIe Gen 5, which we're now seeing roll out on Genoas and Sapphire Rapids, 16 lanes, like you plug a NIC into, is 480 gigabits per second. So there's some great work recently, sort of on the academic side, looking at kind of what the limits are and finding, 480 gigabits per second is really not enough to really drive a 400 gigabit NIC. So if you look at something like the NVIDIA Bluefield 3, actually uses 32 Gen 5 lanes as a special, open compute interface, NIC interface to do that. So that's fine, but we can do it. We've got the PCIe bandwidth. The thing though is that PCIe is just a data bus. So basically, you can read and write memory across the bus, but the two sides of the buses are independent, right? So there's no coherence across them. You read something, it might change, you'll never know. So what this means in practice is that if you want to check if a NIC has a packet, you have to do a PCIe operation. You have to do a read, and that takes 800 nanoseconds. So as people are pushing these super high performance systems, these latencies and kind of the amount of data that can be passing and are starting to become an issue. Another way to think of it is like 800 nanoseconds is approximately 400 feet of cable and propagation delay. It's actually pretty big, right? Say within a data center. So what's CXL? CXL is a replacement for PCIe. Same physical layer, same signaling, same speeds, all that kind of stuff. It's great. You can plug a CXL card into your PCIe slot. Should work. One of the things it does, it simplifies all the protocols down so that, hey, now suddenly the minimum is about 200 nanoseconds, which is good. A factor of 4 is nice. But the sort of more interesting thing, and I'll talk a bit about the implication for this for networking and network cards, et cetera, is that CXL supports cache coherent access to memory. So what this means is that two devices, like your CPU and the NIC, connected over CXL, can have a cache coherent view of each other's memory. Really, in particular, the processor, can of the NIC. And so what that means is that when the processor reads something from the NIC, it can pull that value into its cache, and then if the NIC doesn't change it, it can continue to safely read it from its cache. And you don't have to do a PCIe operation or a CXL operation in order to see that the value hasn't changed. The other side, now the cost of this is the other side, like say the NIC, when it wants to write that value, it has to invalidate the cache line on the processor, and this takes some time. So you can imagine, depending on your expected read-write trade-offs, you can figure out how you want to cache things. So just to give you an example, just try and make this concrete for PCIe. So I've got my CPU and my NIC, and the NIC has a variable in memory, which is what is the tail of the descriptor ring containing packets, right? So what's the last packet I've written? And as it's receiving packets. And so the CPU wants to see, hey, are the new packets? It'll go and it'll issue a read operation over the bus, over PCIe, saying, hey, what's the value of the descriptor tail variable? Get a read result back. Okay, great. Then we actually do a memory read that gets pulled into cache. Awesome. Next time we want to check if there's a packet, we have to do the exact same thing. We have to do a PCIe operation because that value in our cache could have changed. Like, this not in any way tied to what the NIC is doing. The NIC could have written to its descriptor tail and we don't know. So we have to read again. This invalidates the value in the cache. We can then check, oh yeah, there is no packet. Great, there's nothing. So that means every time the CPU wants to check if there's a new packet, it has to read memory over the PCIe bus. So think 800 nanoseconds, it sits there blocked. So with cache coherence though, right, this changes a little bit. So the CPU can read the descriptor tail from the NIC, great, load it into its cache. So it's reading from, in its address space, NIC memory, so it doesn't go into the CPU memory, it's reading from NIC memory. Now the CPU cache references memory in the network interface card, great. Then it can just read from the cache. Now, if the NIC decides, if the NIC receives a packet and needs to update the descriptor tail, it'll send a cache invalidation to CPU. So this takes some time because it can't sort of complete until that finishes, that they remain coherent. But then later, when the CPU goes to read, it no longer has the value in its cache, so it knows it has to do a read. And it does so, and it loads it into the cache. And one interesting aspect of this is that besides things like NICs and GPUs and all kinds of peripherals, there's this idea that CXL and its lower latency means that it can support memory devices. So like a device that just has memory in it. And the whole idea is, oh wait, like if DDR bandwidth is a problem, maybe we can choose our PCIe lanes. They're differentially signaled, they've got lots more bandwidth per pin, awesome. If you look at an AMD Genoa, it has about 4.4 terabits per second of DDR bandwidth and about 4.7 terabits per second of PCIe bandwidth. So maybe we get more bandwidth this way. There's lots of buzz about this. People are writing all kinds of papers. Folks at Microsoft Azure are exploring it. Folks at Facebook are exploring it. One idea is like, hey, let's take a big box and let's put tens of terabytes of memory into it. and then plug it into all these computers with CXL. But suddenly this cache coherent shared memory pool. I'm a little skeptical that this will work, but I mean, I think from the perspective of networks and how systems interact with their network cards, CXL is going to really change how things work in the sense of the speed and the latency we'll be able to get from our NICs actually means that the CPUs will be able to keep pace with how much faster the networks are getting. And so, as I sort of mentioned, cache coherence essentially allows this low-cost coordination between these independent compute devices. Remember, compute is easy, moving data is hard. And so the fact that we can have something like your NIC directly connected to your SSD such that then all the CPU can do is can look in the memory of all its peripherals, which are all cache coherent, and actually you can take the CPU out of the data path such that the CPU can have the NIC directly transfer things to a disk. So imagine this like these network applications, storage applications that don't actually touch the CPU, which is about data transfers using intrinsics between these devices. So in summary, in 10 years, computers are going to look really different. The DRAM wall that we've hit, the scaling wall, means we're going to push towards these three kinds of memory: capacity, latency, and bandwidth. I think the CXL and this notion of actually being able to connect them through a cache coherent fabric is going to be an interesting twist. I'm not sure how it's going to play out, but I'm excited to see. It means we're going to start building these much higher bandwidth applications. We can do things like start moving these large large scale machine learning models. I think it's an interesting and exciting time. So in summary, processors and networks are going to get faster for a while. It's great, but RAM isn't. Cost per bit's flat. It's going to be flat for a while. At least, my guess is 10 years, unless some fantastic new manufacturing process or material appears. There's nothing on the horizon. RAM performance is also flat. And so in 10 years, our computers are going to look really different. The applications they run are going to look different, and this is going to have really big implications to the internet. So it's the end of the DRAM as we know it. I feel fine. I hope the internet feels fine. And yeah, happy to take questions.
My name is John from FutureWay. You mentioned about the scaling or the lack of scalability, considering throughput, latency, and one other factor, cost in dollars. How does power consumption change or vary when you consider all of these?
Yeah, that's a great point. So
thanks.
This is an interesting one. So it turns out that power is actually a really big concern on DRAM. So if you look at DDR5 went from like 1.2 volts to 1.1 volts, and they do all kinds of like crazy voltage regulation where they're just trying to push the power lower and lower because it's about charging those capacitors, right? So yeah, I think also on modern servers, RAM power is significant. I mean, I think you can feed it in terms of like TCO. At least my sense is that's not like you want to store that data. But certainly in terms of individual DRAM elements, right, and heat dissipation and just being able to like, do I just have to put more and more DIMMs, but I can't because at some point I can't run the traces. Yeah, that is definitely. So I guess what I would say is I think that is definitely hard. A lot of the design of DIMMs and DDR is governed by that. But that seems like a problem where we still have leeway, we still have runway, right? People can engineer that. There are other things where like we've got no plan B. So yeah. So person in the back, yeah.
My name is Dmitry. Actually, two questions. First is there are recent and it seems like quite intensive attempts to mix compute and memory. On one extreme, it's something like compute and memory. On the other, is things more extreme example is probably what Cerebras is doing is a lot of cores, very fast on chip, and chip is really big interconnect and some amount, small amount, but very fast memory near each core. So how does it fit into this picture? And the next question, kind of coupled question is that it seems that a very significant part of computing in the near future will be some kind of machine learning, and machine learning has very specific memory access patterns, and in particular like inputs and parameters, they have different access patterns, and probably there are some ways to optimize that and how it's going to influence memory.
Great. So let's go to the first one. So right. So I think actually like an interesting example here is like Samba Nova, right? So the Samba Nova processors, like they're really about, oh, and it's kind of like the lightning bolt sort of great idea there is, hey, rather than have our memory and our compute, why don't we intermingle them? Like we're going to intermingle compute tiles and memory tiles, right? So it's important is in that works really well for streaming computations, right? Where I'm going to actually progress this data through the pipeline. So for lots of like machine learning and data analytics. So in that way, yeah, I think we're going to see all kinds of new architectures. They don't get more memory that way, right? So I think in terms of, if we're thinking about like optimizing machine learning, I mean, look at like what an H100 can do or the TPU can do. Like, yes, we can feed these things. We can bring memory closer to the compute. And that way, I think we'll be able to get and continue to get high throughput on those classes of systems. That's about really like optimizing the compute elements. You had there's another point about the memory, which I was gonna. Sorry, I'm trying to remember the first part of your question. Right.
Yeah.
But I think with respect to like things like smart memories, like I push my computation to my memory itself. If there's compute on the memory cells, that gets tricky, right? Because at some point, computations need locality, right? I have to be computing locally. But look, memory actually isn't local, right? I stripe my 64-byte cache lines across my DIMMs so I can get full bandwidth. So it starts to get a little weird. We're like, wait, I'm actually having, if I wanted to do a computation across, say, multiple cache lines, I either need to, sort of stripe my memory differently to support that, or I actually need to bring the data, to the core where the DIMMs connect.
Yeah, thanks. That's a very good point. To do computation, you have to bring things together.
Right. So I think for smart memory of like, oh, I'm going to do this on a cache line, sure, whatever your striping is. But then that gets into this trick of, your striping now can affect your bandwidth, or what size data item can you achieve your maximum bandwidth. Right. So does that answer your question?
The next question was that there are very specific access patterns in machine learning applications because inputs and parameters they access differently. And are we going to see some optimizations for that?
Yeah, I think absolutely. I think like the GPU and the TPU folks, absolutely. They're pushing that really hard in all kinds of ways. And you also see it for different kinds of machine learning, like graph neural networks have very different access patterns, than say filters over images and convolutional networks. Yeah, people are absolutely, it's not just about optimizing the compute or designing the compute. It's also even designing your memory controllers and your memory layouts. Absolutely. I think we are seeing that.
Thanks.
Yeah.
Hi, Jonathan Hoyland, Cloudflare, not a hardware person. Is there ever going to be a world where we just write data to the network and round trip it just to store it?
And well, I mean, I think lots of data centers do that, right? In the sense of like with the decoupling of disk. So when your network latency is 100 microseconds and your disk latency is 10 milliseconds, right, for a seek, there's no reason to keep, this is the whole disaggregation of like, we have big storage units and then compute is separated from that. Again, what I'd say though is just remember, like compute is cheap. So storage is different for that reason, but compute is cheap. Moving data is what's expensive, right? That's what takes power. That's what takes time. And so there are two basic ways you make computation fast. Number one is you parallelize it. Number two is that you keep the data local. Like that's all there is. And so the idea of, oh, I send stuff out, to store it, sure. Or are you talking about like I just make it loop through the network?
Yeah, you just have a fiber that points at itself.
Well, so let's think about like propagation times, how much storage you get. You don't get a lot. Now, there are actually people who think this way. A lot of supercomputing people think this way when they're doing like super high data rate, think many terabytes per second. They actually think about the propagation delay along their fiber as that is the data like that actually counts as data that's in storage because it starts becoming significant. Yeah, so they think that way. But I don't think you don't necessarily want it like circling around on this fiber optic cable just to store it, right? So
So if it's easily parallelizable, why not, right?
Well, you have to build the ASICs to drive all that, right? You have to pay for those. So
Thank you.
Thanks. Nalini Elkins, Inside Products. Now, this is something probably, which is probably way, way out there and probably more than 10 years out. But I know there's some research being done at University of Washington and also Harvard for putting doing what they call hard soft memory, which is using DNA to store memory. I mean, it's like, I don't even know how you do like what's the manufacturing process here? You know what I'm saying? Like, yeah.
yeah, I think there's so there's actually a really nice keynote by gosh, I'm forgetting his name. University of California, Santa Cruz. Who's like a total like storage, wizard. And he talked about all the different media that are out there, and he has this great thing of like latency, capacity, cost, etc., durability, and he draws this, sort of one of these like multi-axis star things. And he says, look, if a memory ever encompasses another, then the old one goes away because it's just better in every way. And so he looks at stuff like DNA, but also there was some stuff that came out of Microsoft on like glass etching, right? Etching in glass and the precision of that, which tends to have better durability than DNA. And so he looks at all the different possible storage things. But I think you're really not talking about storage, like what's after Flash, right? Flash has, they're continuing to do more and more layers, right? That has some legs. We'll see where that goes. But yeah, I can't say too much about the future of storage. Ethan Miller is the person. Ethan Miller is he's got a great keynote talking about storage. He'd be a good thing to look up.
Yeah, thank you so much.
We out of time?
Yeah, we'll take one more question.
You're the
Hopefully
tail of the queue.
Cool.
Right.
Tell everybody.
Yeah.
Rich Solz-Akamai. So thanks for this talk. It was really informative and frankly terrifying. And I wanted to push back.
Oh, it's so exciting for me. There's so much research to do.
Well, yeah, but I got to write the code. So my question was I wanted to push back on the very last sentence you said, which is, and I feel fine. I mean, I can understand, when Moore's law started to die off, I guess it's still kicking a bit. It's like, okay, I know how to do things in parallel. That's a lot easier. But now I have to think more specific. I mean, I can understand accelerators and that's easy, but now you're talking about, well, accelerators and smart memory and dumb memory. I mean, do you really think it's going to be okay?
Yeah, I mean, I do. Like, people are smart, right? They'll come up with ways to do it. I mean, so one thought is not necessarily that any given application is going to have to do all these things, because that's not true. Like, if I'm looking up things in a key value store, like, I'm not using a TPU to do that, right? It might be that the composition of applications then does this. A lot of it, I think, is going to be, we're going to start becoming much, much more careful about our data structures, right? Like, maybe we'll go back to the 1980s, where like we really tried to make them small and tight, and it's not just RAM is free. So in that way, like, I feel fine. These problems, the challenges that the engineering challenges this will raise for us we've lived in worlds like that before, and we've been okay. I mean, it means that, like, the free lunch of everything getting better all the time is going away, but like, oh, that's engineering. So
thanks.
Okay, let's thank our speaker, Phil Levis, again. Annette, please come up. Yeah, please come up. Okay, so our next speaker is Annette Bramlin Barr from Tel Aviv University, and he's going to talk about it's not where you are, it's where you're registered, IoT location impact on MUD.
Yeah, hi, thank you for the introduction. Yeah, thank you. Okay, so my research is titled, It's Not Where You Are, It's Where You're Registered, IoT Location Impact. And this research was done in collaboration with Anat Bremler-Bar from the Tel Aviv University, with David Hai from the Hebrew University, and Shoam Danino from Reichman University. This research was also supported by Cisco and the Israeli Research Authority. I would like to express my gratitude to the NRW chairs and the committee for allowing us the opportunity to share our findings today. So we started this research when we try to understand what are the factors that affect device network behavior, IoT device network behavior, actually. Yeah. And the first scenario that we thought about is this scenario in which there is the same device in two different locations. And when we say two different locations, I'm referring to IP-based location. It means the geolocation of the external IP of the device. And we found out that the impact of the IP-based location is on the network behavior of the device, and we saw an impact on the network behavior. So we're talking about IP-based location, but actually, what it is it even more impactful is the user-defined location. And we define the user-defined location as the location that the user chose through the registration process of a new account. And in that case, we have a scenario in which we have a device that is located in the UK. It's physically located in the UK, but the user chose to register it in the US. You can see that there are three options: the American server, the European server, and the Chinese server. And can I use the laser? Okay, yeah. And there are three options, and the user chose to work with the American server. So in that case, there is much more impact on the device network behavior, and we will see it very soon. But when we have this kind of finding, we thought, why do we care? So what are the implications of this finding, that there are different device behavior, this different network device behavior for different places, for different locations? So the first implication is on the network security framework, MAD IETF, MAD RFC 8520. And in that security framework, we define a profile of the device, a network profile of the device. And if we would like to understand what is the profile, we should take into account all the factors that affect it. Another implication is on IoT identification. If we will learn our data set, we learn in one location, in a single location, and then we will try to identify the same device with the same firmware on another location, it just won't work. It might be potentially with errors. And essentially, each task that is composed of learning normal device behavior and then extracting rules such as the network security framework and extracting features such as IoT identification is affected by this finding. So these two just are two like trailers for the rest of the presentation. So I go over briefly over the outline for today. So I will show you that user-defined location is much more impactful than IP-based location. And I'll show what is the implementation. How does user-defined location is implemented in the common case. I will cover background about MAD, about the IETF security framework, and then the implication on user-defined location on MAD. And then I'll show you a proposal that we suggested to improve the implementation using extension features of DNS. Okay, so as I said, location impact is very common. And when we came to quantify what is more impactful, IP-based location or user-defined location, we created a similarity measurement, very straightforward similarity measurement in which we compared the two sets of domains for the same device with the same firmware at two different locations. And we defined two types of location: the IP-based location, which is the geolocation of the external IP, and the user-defined location, which is the location that the device, that the user chose through its registration process. And as you can see in the comparisons, you can see that in 90% of the comparisons that we made in our data set that compose of dozens of devices in up to 10 locations for each device, we found out that 90% of the devices exhibited a difference in the network behavior, but just 54% of the devices exhibited a change in the network behavior when we change the IP of the device, the external IP of the device. So then we raised another question was raised, and it was why there is a difference in the domains. Because the similarity measurement measure the difference in the domain, the set of the domains that the device uses. And different domain names, we saw through our research, through our data set, that different domain names allow different features and servers. And for example, we saw a camera that as a feature that was available only in China. Only that when we chose the Chinese server, the facial recognition feature was enabled. While you choose, if you choose the European server or American server, this feature was not available. But there are other ways to implement different IPs or different servers for the same domain. For example, using IP-based location. And in the next slide, I will show you how DNS can support IP-based location decisions. But now we understand that in order to allow the user to decide what is the location and what is the features that he wants to, the domain names must be different. And here you can see the IP-based location decision using DNS. So in that case, you can see that the device is located in the UK, but registered in the US. In that case, the device uses an api.smartthings.com, this is the domain that it uses, and it asks the recursive resolver, which is located nearby the device in the UK. In that case, the recursive resolver sent this request in his turn to the authoritative name servers, and because the request came from the UK, from the UK resolver, the IP is from Ireland, which is in the UK, and that is how IP-based location can help, DNS can help to make IP-based location decisions. We call this kind of domains, domains with no location identifier within them, we call it global domains. And in the next slide, we can see regional domains. In that case, it's the same case that the user registered in the US, the device is located in the UK, and the device initiates a DNS request to the DC-US East. It uses a US server, and despite the fact that the recursive resolver is in the UK, the authoritative name server knows to answer with an IP from the US. And we call this kind of domains regional domains, domains with location identifier within them. And that is how user-defined location is implemented. And this is how user-defined location difference looks like. In the right side, you see the same example in which the device is registered in the US, and the device uses the useast.connect.smartthings.com and gets an IP in the US. While on the left side of the slide, you can see that the device uses another domain, a different domain, which is euwest.connect.smartthings.com, which is another location, another domain with a location identifier within them. Another thing that I would like you to keep in mind is that there are not just two available locations, there are much more. You can capture it, in the app, you can choose up to 10 locations. In this case, we capture the device in up to 10 locations. This is the YI camera. We created a similarity heat map for the similarity measurements that we made in up to 10 locations. Each cell is compared to different location. And as you can see, despite the fact that you can choose different places, you can see that there is a region actually. So different places are addressed to the same region, Russia, United Kingdom, and Germany, for example. And what I would like you to keep in mind is that there are more than just two options. I presented in the previous slide just two options to simplify the slide. And as I presented, the common case is in the subdomain. The differences of the domains are in the subdomains. Only 9% of the domains present a difference in the top level domain. The top level domain is the .com, the extension of the domain. Okay, so now we saw that there is a difference, that it is caused by the user decision. Let's go over the MUD profile, MUD, the IETF standards, RFC 8520. This is essentially a network framework, a network security framework that defines a MUD file. And MUD file is essentially an access control list, a set of access control entries that composed of the legitimate endpoint, the protocol, the source port, the destination port of the device uses. And the whole logic behind MUD is to reduce the attack surface on the device using a firewall or any network gateway that supports MUD. The whole logic behind defining a MUD file is that in IoT devices, there is a specific goal for each device. Think about a light bulb or a a water sensor. These devices have a specific goal. It uses a small set of domains, so it makes sense or reasonable to create this kind of file. It won't work for computer, for example. And now we can see what are the implications on the MUD framework. So if we have a device if we will create a MUD file for the device that is registered in the US, it will compose of these two domains, the US East domain, and on the UK, it will create an EU West. But the implication is that the learning phase of the MUD will be much complicated. It will be, we will need to capture the device in every single location that the device supported. We need to combine maybe all rules into a single large MUD, or we should use separate MUD files for each location. And what about the explainability? How can a security administrator go over this MUD file and understand what is going on with this device? And how can the manufacturer or the security administrator can maintain even this kind of location? And as I said, there are more locations than just two. You can see that like this MUD file can be available for many more. So the next thing I would like to share is about DNS. So there is an extension for DNS that is called ECS. ECS stands for Extension DNS Client Subnet. And actually the easiest way to understand it is through the figure. So in the figure, you can see that the device is located in the UK. It uses a domain api.smartthings.com. But in that case, the recursive resolver is in the US. It happens sometimes that the device uses a not nearby recursive resolver when you use open resolver. And in that case, when the authoritative name service will get the request, he will answer with a US IP because the recursive resolver is in the US. So to solve this problem and to get the IP that is nearby the device itself, there is client subnet. In that way, the recursive resolver will add a field, an ECS field, that mentions that the device itself in the red frame, the device itself is in the UK. And that way, the authoritative name servers will know to answer with a UK IP. And we also know that ECS, the RFC of ECS allows the endpoint itself, the device itself, to add this ECS field. And that led us to our proposal. In that case, we want to solve the problem of having different domains for the same actually server behind. And instead of using different domains, we can use a single domain and use the ECS in order to carry the user decision. So instead of using the ECS by the by the recursive resolver, the device itself will add the ECS field. And instead of mentioning the IP-based location, their relocation, the UK, you will mention the user-defined location. And in that case, the authoritative name server will know to answer with the US, with the American server, and not with the UK server. And of course, we will use it just for the regional domains and not for the global domains in order to preserve the behavior of the device. And that is how MUD looks like when we use this proposal with the ECS. In that case, the learning phase of MUD will be much easier. We will need to capture it just in one place, and instead of like go over all over the locations that are available, we can use a single MUD as expected, as predicted in the RFC in the beginning, and it will be much explainable and maintainable to have it that way. So I made it very quickly. Let's go of the summary. So user-defined location has an impact on the IoT device network behavior and specifically on the domains set that the device uses. IP-based location has also an impact, but less than the user-defined location. Dataset and security measurement should take into account the location. Otherwise, it just won't work. We won't be able to defend the device or to identify it when we are talking about IoT identification. And user-defined can be implemented instead of using different domains, using the extension DNS. And that's all for now. we have some more resources. So you can scan the QR code about IoT networking, about MUD RFC. We have tools to generate MUD. Anything about IoT network and IoT network behavior is in our website. Thank you very much for listening.
Any questions? There's no one in the queue, so you could come up. Oh.
Hello, my name is Ayub Missus from Fujitsu Research of Europe. Thank you for your presentation. I have a quick question related to what would be the impact of using VPN, for instance, to, I would say, countermeasure this kind of solution. What do you think about that?
Yeah, so VPN can change the IP-based location. So actually, when we made this research to quantify the IP-based location, we used VPN in order to simulate the device location. So even when you change the location, the IP-based location, using a VPN, still the user can choose a specific location in the registration process, the user-defined location, and in that way, the VPN just won't have any impact. The user-defined location is the impact factor. Is that answered your question?
Yeah, kind of, but if the user it was the user who's creating this VPN in order to avoid like selecting different servers. What my question is that because I have some background related to new like technologies for IP-based geolocation. One of that it's like based on probing technologies. So I don't know if you consider this kind of approaches.
So our research is we measure the IP-based location. So if you fake it using a VPN or any other way, we will take just the IP base that you fake with the VPN. So we didn't try to find that you're using a VPN.
So basically, as a next step, it would be interesting to consider detection of proxies.
Yeah,
or VPN.
this is something that we can see, but actually what the manufacturer does here is to allow the user to choose. So they don't want to restrict the user. They want him to allow the user to work with the device. So like,
I guess we can have this discussion later on,
sure.
because we do have this topic. We are working on this kind of detection
Great.
tools. I will share with this insight with you later on. Thank you.
Thank you.
Hey, Phil Levis, Stanford. So as you just mentioned, the companies want to allow someone to choose which server they use. Can you talk about the regulatory and legal implications of that? Because this actually seems in some ways counter. Like, I mean, of course, VPNs can allow you to escape IP, but just, I mean, at some point, you know, you turn on your facial recognition in the US, right, is a little tricky.
Yeah. So actually, I'm from the computer science department, not from the legal department. But
yeah, but I hope you thought about it. I'm not asking for an answer, just your thoughts. Right?
So actually, I think that I don't need to explain when they vote. Can we zoom to the? There is no option. Okay. So what you can see that is written over there is that you can choose the European server when you want to work with countries that support the GDPR. And you can choose the American server when you don't want to work with the GDPR, and you can work in China when you are in the Chinese mainland. So I think that they are explicitly mentioning that you can choose if you want the GDPR to be enabled or not. I'm not sure if it is legal or not. I guess that they have their own legal considerations.
Sure. Yeah. I mean, I think there's so they push the liability to you, right? All right, thanks.
Thank you.
Okay, let's thank our speaker again. Roman, please come up. Our next speaker is Roman Balchukov from UC Santa Barbara. And his talk will be Pinot, Programmable Infrastructure for Networking.
Yes, thank you for introduction. Can I get this? My name is Roman. I'm going to present the Pinot Programmable Infrastructure for Networking. It's a joint work with my colleagues from University of California, Santa Barbara and Nixon Incorporated. And I want to start on this slide from pretty bold statement that one of the problems in the academia for network research are representative infrastructures. Pretty often researchers end up with what they have in the lab. currently it's like a couple of laptops, several routers, switches, etc., what they have, and they're trying to create something representative to collect the data from. But the desired infrastructure is something that you can see on the right side of the slide. It should be more complex, more, let's use the word representative here, because it depends on the actual experiment that a researcher want to conduct. So non-representative infrastructures lead to non-representative data, bad data, and bad data, especially if we are talking about machine learning solutions, lead to bad solutions that we cannot apply anywhere. And if anyone interested, we have a paper regarding bad data leading to bad solutions recently. So the question is, like, what we can do with it. Fortunately, there is a number of existing platforms. This is a non-exhaustive list of different platforms like RIPE, Atlas, Cosmos, Metrics, Measurement Lab, and kudos to them for allowing to do the research experiments, etc. But they are great. But there is a simple problem. Imagine that we want to conduct some experiment. And I want to say that some experiments are hard or even impossible to implement on these problems. Let's start with a pretty simple example. I want to measure quality of experience for YouTube. For this, I want to watch the YouTube stream. I want to collect network data, like raw packets. And at the same time, I want to measure things like amount of buffer health, how many times video was stalled, quality of the video, resolution, etc., etc., etc. Okay, that's pretty simple. But then it starts to be complicated. For example, I want to do this over wireless network, and not of many of such platforms allow you to do this over wireless networks. And I want to do it in a live network with the different users when I have a traffic aside. And I want to do it over a long time period, not just once, but like in several weeks or even months probably. And as well, I want to do it with a flexible and programmable client to dynamically change videos, resolutions, and what I'm measuring. And I also want to separate backbone problems from last mile problems. So, and now it becomes very complicated. And the question is, what infrastructure do we need for all of this? And we decided that we'll implement our own solution. And this solution, basically, I will present on the next slides. It's programmable infrastructure at University of California, Santa Barbara. I will describe on the remaining slides why we did it, how exactly we did it, and how to reproduce if anyone interested on their campus infrastructure. So what are design principles for all of this stuff? At first, we want to be able to measure things actively and passively at the same time. That's pretty important. I'll describe benefits of it on the other slide. The next one, we want last mile connection to carry real world user traffic. And I want to say here that campus networks are pretty interesting for this stuff, because campus networks allow you to have balance between unrealistic lab scenario when you have a couple of devices or maybe even 10 devices, and production network that academia usually don't have access to because it's production network. So campus scenario could be very interesting in this case. Campus network can mimic typical enterprise network. For example, University of California, Santa Barbara hosts around 25,000 students, not counting administrative staff, professors, and everyone. And campus network, at least at University of California, Santa Barbara, is vulnerable to different things like the normal provider network. Latency spikes, peak hours, user and traffic overloads, especially during summer. There are no users. During winter, for example, during different exams, there are a lot of users, etc., etc. So you see different patterns in this network. What else we wanted for our infrastructure? We wanted localized deployments, so nodes would be close geographically and logically. We wanted to support arbitrary experiments, like literally anything based, and we want direct and fast access for our researchers so they can iterate on their hypothesis fast and do not wait in a queue or something like this. And in addition, of course, we want to do everything ethical, so minimal disruptions or no disruptions to existing users, preserve privacy, and to make everything fully reproducible, to use off-the-shelf components, cheap components if it's possible, and open source everything. So basically, these are principles of our platform. Very brief slide regarding the overall architecture. Basically, it's separated to two parts, the campus part and data center part. On campus part, we deployed dozens of Raspberry Pis that are using UCSB Wi-Fi infrastructure. I'll describe it a bit more on the next slide. And we do active measurements from these devices. At the same time, at the data center of the University of California, Santa Barbara, there is a backbone, basically traffic and infrastructure. And on the border gateway, here on the top of the slide, we have a live traffic mirroring to our servers that I also describe later on the next slide. So we basically have active and passive infrastructures deployed together and measuring together what we want. And I want to start from active measurements, how we implemented it. As I said, we took Raspberry Pi devices. These are single board computers with the Linux on top. Basically, we used Ubuntu optimized for Raspberry Pi. We deployed 60 of them, something on the campus and different locations, and we will deploy 40 more this month, and no one can stop us. They are controlled from a central server by SaltStack. They are deployed in public places such as libraries, dormitories, university centers, basically where students are located most. And very important point here that University of California, Santa Barbara has a single Wi-Fi spanned over the whole campus. And many universities have the same wireless infrastructure. And our devices use these Wi-Fi, and that allow us to claim that their traffic is more or less representative as a typical user of this Wi-Fi network, because they use the same access points and they suffer from the same problems as all users suffer around. Here is the example of the device. It's even a real world device. I mean, you can probably scan QR code and get some statistics from real time. Regarding deployments, we deployed them over the whole campus. Mostly these are different dormitories and university centers and libraries, etc., etc. We try to cover almost everything, and more is coming, basically. Regarding passive data collection, so how we implemented passive data collection? There is a border gateway of University of California, Santa Barbara. We agreed with the IT department that we will have a live traffic mirror from this border gateway to our Intel Tofino switch. It's a programmable switch. On this programmable switch, we implemented ONTAS program. It's a P4 program for anonymization of the traffic. Basically, it anonymizes IP addresses, MAC addresses, and everything to remove possible source of identification of the user. And this also allows ethical review committee to check that we are really doing this anonymization and everything. And then Tofino switch balance this traffic to our servers, where we just basically run speed dump with additional stuff to collect all of this data and save the data. More details are available on the website, up to the configuration and links and GitHub repositories, etc. So why exactly active and passive measurement? Many platforms implement just passive measurement. Some platforms implement active measurements. Active measurements are important because in the world of encrypted traffic everywhere, and I love encrypted traffic, but we still need some labeled data, especially for machine learning algorithms. And for this, we need active measurements because we can control labels. We also need passive measurements because we cannot create live network traffic without passively observing what's going on, without user traffic, basically. And the combination of active and passive measurements on our campus allow us to do two things, very important things. The first one, it's pretty unique observation of the packet from multiple vantage points. So we can look at the packet on the border gateway, we can look at the packet on the device itself, and we can find out if there are any problems on the backbone of the provider, or there are problems on our campus. We even can get the information from access points, Wi-Fi access points, and maybe find the source of the problem there on these access points. And the second one, if we have some data that we initiated from the active measurements, from active devices, and we found some patterns, we can use passive observation to confirm these patterns, to check that these patterns really exist in the real world user traffic. That would be easier to find because we already identified them from the originally active measurements. So if you want to implement the same infrastructure at the other campus, for example, you can implement them separately because they are used more or less independently, but together it's more interesting. Some examples of current experiments, as I mentioned in the beginning video, quality of experiments for different platforms, YouTube, Twitch, Vimeo, etc. We tried and still trying to do quality of experience measurements for video conference platforms, for Google Meet and for Zoom. We use this infrastructure for controlled speed tests, where we can control time, whether it would be in peak time or in a pretty calm time, interface, wired versus wireless, location, whether it's busy location or pretty empty, etc. We can use this infrastructure for application traffic collection for fingerprinting and even for botnet imitation with different networks attacks. And the IT department was not happy about it. What else? Yes, there is a slide of different limitations of this platform. The first and very important one is that these theoretical data guarantees of the campus networks are only theoretical. So they're debatable. And the only solution we know for now is to measure and explore and confirm whether the data collected from this infrastructure is representative for the experiments that we want to collect this data for. But at least we think and claim that this infrastructure would be more interesting than the lab deployment. Ethical review is important and required, so if you want to do the same, please do it earlier. And most of the other problems are either administrative problems, where you want to do stuff with university, or security problems, where you don't want your deployment to become a botnet without your knowledge about it. And so at last, we want to claim that we've created all of this stuff. We want to say that this infrastructure is pretty interesting and representative and interesting for research, for network research in academia. It has live user traffic and many universities have many users. So it's if you are trying to reproduce it, and we encourage you to reproduce it, it would be more or less useful for you for research. It's cheap, especially Raspberry Pis. They are pretty cheap, and to deploy everything, it's pretty simple. All hardware components are easy to buy. Well, servers could be expensive. And on our website, we have a separate page for reproducibility, where we have all links to Amazons and everything, all configurations, all GitHub repos, up to the code for labeling our devices as well. And pretty important part, we invite other researchers to participate in this experiment, to submit your experiments, and we want to cooperate with you and provide the platform for you as well. So there is an email where you can go, where you can mail us, or go to the website and find the same information there. And that's it from my side. Thank you so much for the attention, and I want to answer your questions if you have any.
Thank you. Greg Mirsky Erickson. Very interesting presentation. Thank you. So you mentioned that you use a combination of active and passive measurements. So can you clarify what active measurement method you use?
What exactly do you mean by active measure method? We have Raspberry Pi devices. They have basic Linux on board, Ubuntu, and this allows us to do any measurements that you can do basically on Ubuntu device. So from speed tests to implementing custom scripts on Python that you can run basically anything.
Okay, so basically it's not that you're using, for example, T1 polite or STAMP protocol.
Yeah, it's not some defined protocol. It's basically open platform for implementing anything.
Okay, but okay. Are you using any particular measurement protocol this time?
No.
Okay.
We using a particular platform for submitting experiments, NetUnicorn. The details are also available on the website, but that's the only restriction that we have. And most often we do experiments in Docker containers that also create some restrictions for researchers. You don't have usually access to raw device and Wi-Fi statistics, for example, but it's for security restrictions.
Okay. So have you given a thought of using hybrid measurement methods like in situ OEM or alternate marking method?
Not yet, but probably now, yes. Thank you for this. Yes.
Thank you.
And if you don't mind, I'll talk to you later regarding
Sure.
this.
Thank you.
Thank you.
We can only take one more question. Royal Yanagida.
Hi, Rio Yanagida from University of Glasgow. Thank you very much. It was very interesting. So I think I see the rationale of how it's difficult to do network research, involves our large infrastructure, provided more sort of real life sort of scenario or situation. I get that bit. What I'd like some clarification is on the reproducibility. What do you really mean by reproducibility in this context? Because it could mean a wide range of scale of reproducibility. So do you mean it in a sense that you can do similar thing if you implement it with the bits of code we have, or are you saying you can redo the experiments and then get a similar behavior, which I don't think is quite possible?
Yes, it's not quite possible with a live network.
Right.
Regarding reproducibility, I don't remember whether reproducibility here on this slide. Reproducibility means reproducibility of the platform itself, not of the experiments. I mean, we have a web page on our website where we show, where we describe all our GitHub repos, all our how our websites are built, how the platform is built, what components are used, what servers, specifications, and everything. Regarding reproducibility of experiments, it's a separate topic, but basically Docker-based solutions plus Net Unicorn platform that we are using allows us to have reproducible code for experiments and basically reproducible pipelines. And it's not reproducibility in terms of having the same traffic each time you run the experiment, but at least it's reproducibility that you expect the same behavior during each time you run the experiment, that your experiment will have the same behavior.
Okay, thank you.
Thank you. Yeah.
Sorry, we have to take the other questions offline. Next speaker is Tobias Feibig from Max Planck Institute for Informatics. And his presentation is Crisis Ethics, Reliability, and Measurement Network, Reflections on Active Network Management in Academia.
Okay, good morning, academics, engineers, and other people from the internet. I'm Tobias Feibig. You might know me from other fun research like Darling I put or University IT in the cloud, and now Zoom tells us what to do in our seminars. Or without feminist culture, you won't have IT security. But today I'm talking about, well, a little bit of ethics, a little bit of reliability and crisis and measurement network. So first, network measurements. Well, that's basically what we are doing. It's an important tool for academics to get their papers. It's an even more important tool for practitioners to understand how things work on the internet. And they come in active or passive form. And usually, especially the active ones, are somewhat difficult. If we're measuring things, for example, emails, these things got a little bit more complex. If you were measuring email in 1991, you had RC821, 822, a little bit of DNS like 345. And if you were really into funny protocols, you could also get a couple more from X400. If you're doing this in 2022, you have around 500 mail RFCs, 300 DNS RFCs, HTTP for MTA-SDS, which is far too many. Of course, there's also all the stuff on TLS, and well, IPv4, IPv6, welcome to the MTU world. So this got a little bit more complex. The other thing is, if you do these measurements, you, for this complexity, have to write reliable measurement software. And little example from my own mail server. So one morning I woke up and saw this. So I basically saw that I had no SMTP anymore, that my MySQL daemon was handling around 400 queries per second, and my OpenSMTP, the mail server, was running at 100% CPU. Solution to that was that I had used a MySQL backend with the default collate of MySQL, which is Latin 1 Swedish CI, and some nice person did some active probing involving UTF-8 characters of count passwords on my server, which led to a funny loop of the authentication module of OpenSMTPD breaking off with this warning you see on screen and retrying then, which basically saturated the OpenSMTPD. And if you write measurement software, it's really easy to find similar things. So the internet is full of corner cases. We have to account for them. There's a lot of unwritten rules about how you hold protocols. And ideally, you want, for your measurement tools, reuse things that are already tested and deployed software. In general, if you write software, you really benefit from being a good and experienced programmer. And well, you don't want to break things that are not standard compliant. You have to do all the basic things like version control tests, proper development best practices. In addition to that, you also have to run your measurements. And here we have a YOLO-COLO example of a measurement you might see, which involves some scanning, a recursive DNS server and an authoritative DNS server. And if we look at that, we see there are funny things because the person who set this up apparently forgot that DNS also comes in TCP. And there's a lot of things that can go wrong here. Also, our DNS1 might stop resolving. Maybe DNS stops being delegated to our authoritative name server, or our recursor is just stubbing against one of the quad 1 servers, and we see queries from ourselves on our authoritative server and think that they are part of our measurements. So if you want to run measurements, you also have to be an experienced system operator. You have to have an understanding of all the tools involved. You have to monitor your stack, historic and real time. Basically, make sure that your setup is self-contained. Well, you just have to do all of that. So Then we also want to do ethical measurements, which means we have to consider all possible unintended harms. And especially with the internet full of corner cases, there's often the case that it's like, yeah, we know the internet is made from duct tape and bubblegum, and this specific thing would be an issue, but we kind of decided not to talk about it because otherwise things break, which is something I heard, for example, about colleagues' work on the aggregation of a /32 and putting it into the GRT. We have to get ethics approval, usually from people who are academics in an IRB or ethics board who have no clue about the internet. We have to do all the probe attribution things, so the reverse DNS, the RR, who is running web servers, etc., etc., etc. We have to do app use handling, and we have a maintained block list. So the PhD we need is somebody who thoroughly understands the protocol stack they are measuring, is versed in all aspects of IT operations, experienced programmer, experienced system operator, and let's be honest, this is not a PhD student. This is basically a whole IT department. The thing is, PhD students tend to be people. This is sometimes a surprise for faculty, but PhD students are actual people. And if they are facing this world of requirements in the reality of a PhD, they are facing a world of these requirements under 4 to 8 years, which they have for their PhD, where they have to do 4 top-tier papers, try to do new research advancing the field, have to embed this in related work, and usually do this directly after their bachelor or their master. If you do the math, 4 years and 4 papers, the first paper should be under submission after 1 year. This leaves around about 6 months to basically get 2 decades, 3 decades of protocol development into the brain of a single person. So what people then usually do is this. They over-caffeinate and they take shortcuts. Because a very basic rule of everything is that people will do people things. And if you put people under pressure, they will try to cope. And if they cope, they cut corners. And that then makes bad measurements. The idea would, of course, be that faculty can help. The problem is the perception of many PhD students is that their faculty is not necessarily helpful in giving good advice. The other thing is, if you think about junior faculty, there is something very, very important, which is called the tenure clock, and they tend to be running after that. So they are doing service because that helps tenure. They are trying to write grants because that helps tenure. They are trying to get publications because that helps tenure. Well, you get the idea. Professors, on the other hand, we are still lacking any kind of evidence that being a tenured professor actually changes the amount of time that is available to you. Usually it's the same as for a non-tenured person, amounting to too little. And then there, of course, is the thing, if you become a professor, you become a manager, and you basically get a bit removed from the technical world. So in the end, you might not actually even be versed enough to work on these things. In an ideal world, of course, you would have some form of IT support or former students handing things over. The problem is that research program is not really a well-established position in most universities. And well, university IT, often difficult, often riddled with middle boxes, funny FortiGates on campus. Usually you make a lot of acquaintance with your university's IT department if you run active measurements, because basically everyone crashed their Fortinet once or twice. Also, infrastructure, if a student left, it becomes undocumented, so the next students build their own. What we are basically proposing, or I, given this is a single author thing, is that we build a community-governed scan infrastructure which is available to researchers, where measurement tools are reviewed by people that are not only academics but know what they are doing. Basically take away the overhead of all this measurement running, like app use handling, block list maintaining, etc., 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 and enable basically people to focus on their research and make better network measurements. Before closing this talk, a couple of Q&A so we get quicker through the Q&A. First question, of course, is why am I doing this alone? Well, it's a relatively simple reason, because I have the experience with joint projects that it's better to have something running, and otherwise you end up in bike shedding. So I want to build this and then hand it over to somebody who can run this. There's, of course, a question why not some US R1 university group should run this, but instead I'm trying to build this and give it to a public body. Well, it should not be owned by an entity that publishes for a living. Currently with me, that's of course the case, but I want to change this. Researchers tend to be a bit paranoid of being scooped. Who should be running this? Well, entities would be the RIPE NCC measurement working group or MapRG, or of course the IETF, but as soon as it works, I will start looking. Isn't it easier to block if we give this entity a fixed prefix? Well, it's kind of the point, because usually in active network measurements, you end up with a problem that you get scanned from Amazon, you block that, and a week later, the learning management system of the university is at that IP, which is kind of not nice. What if it doesn't work? So if I don't get this together and don't make it work, well, basically I burnt my own time and money and no one else is hurt, which is also always kind of nice. How will this be paid for? Well, for now, it's supported by the Tobias Personal Bank Account Foundation for doing things I consider useful grant. By the way, not accepting other applications. And additionally, to operators indirectly sponsor upstream, I got a /22 IPv4 legacy from the MPI for Informatics for the project. And as soon as things are up, I will also try to motivate more entities. And last slide, where can we find this? Well, there already is a couple of resources which are also in the GRT. There's basically 2 POPs already, Düsseldorf and Berlin. There's 2 planned POPs doing something in MPI informatics to have a bit more infrastructure going and something in Amsterdam. I need collocation, hardware, and layer 2 between POPs. And on the web, there is a website which is currently a static file, but I'm working on something more interactive and some existing services. And with that, thank you, and I'm happy to take any questions.
Very interesting talk. Any questions?
So if you're all collecting your pitchworks to find me during the break, that's also fine.
Hi, Colin Perkins. So clearly you're not wrong. However, I wonder if the process of running this is easier than the process of running the measurement infrastructure.
The process of running
the process of administering and managing the foundation and managing how to get people involved and so on. Someone has to do this, and someone has to coordinate with all the people who want to use the infrastructure and so on. And you're bringing in a whole nother layer of management overheads. Is this easier than actually building the infrastructure?
So I will try, and I will, well, the governance part will be harder than just building the infrastructure. Okay. But the problem with the infrastructure built by everyone, that not everyone can do that. And not everyone has the experience. So doing it in one spot once is probably easier than people reinventing the wheel everywhere. Even though for IT, reinventing the wheel is kind of a standard practice, granted.
Okay, thank you.
Okay.
If no other questions, let's thank our speaker, Tobias. Thank you.
Thanks.
Okay, so this is the end of the first session, and we'll see everyone in the afternoon. Thank you for coming. No, it's my first experience. You've been to